Welcome all. Happy morning, afternoon, evening to you. This is Kannan. I'm one of the co-founders at Yugabyte, and I'd like to welcome you to the third edition of YFTT, the YugabyteDB Friday Tech Talks. And it's my pleasure to introduce today our speaker for the topic, YugabyteDB Sharding Strategies, and it is Bogdan Matican, one of the very early engineers, the very first engineer, I would say, founding engineer on the team. And I've had the pleasure of working with him now at two places, back early on at Facebook, and now again at Yugabyte. So with that, let me just welcome Bogdan. Would be great if you could share with the team what you do at Yugabyte and a little bit of the overview of the components that you're primarily responsible for.
Oh, definitely. Thanks, Kannan. And as a small aside, yes, we've been working for a while. You were actually like my intern mentor all the way back in Facebook many years ago. So we have a long-standing relationship there. As for the topic at hand, so I work at Yugabyte. I manage the distributed storage and transactions team, which for a short version of it would be the bottom half of our database product. So we are responsible, as the name goes, for everything from single node storage to distributed system problems, two-phase commit transaction protocol, cluster coordination, reliability, stability, overall health of the underlying storage subsystem. That's probably the shortest version I can give painting the team. Sharding, obviously, being a big component of that, and that's what we're going to be spending most of the time today going over.
So let's get started, Bogdan, right into the topic, and then hopefully we'll save some time at the end for questions.
Definitely. Okay, so for today, we're going to be spending most of our time talking about sharding strategies in YugabyteDB. But before we go into that, maybe high level, what is sharding, or what do we mean when we talk about sharding? Essentially, it is the process through which, if you think of a large user table with a lot of data, let's say maybe it doesn't fit on even a single node database. For a distributed database like Yugabyte, at that point, you would actually want to consider distributing your data across multiple database nodes. So a prerequisite of that would be to take your input table and chunk it out into smaller non-overlapping pieces, which would then be called shards. Or in Yugabyte terminology, tablets, as in pieces of a table. And once you have these shards, you would be able to take each of them and spread them across database nodes in an effort to better distribute load. And maybe a small asterisk here of what actually would be considered load. You would be able to spread both overall storage, because each shard might hold a different number of rows and implicitly have a different size on disk. But you'd also be able to spread load in terms of user operations. Like maybe not all shards are getting the same amount of write traffic or read traffic. And that is also a factor that comes into how you're thinking about your sharding strategy. You also need to factor in, maybe this is a prerequisite of sharding, but essentially each row in your user table is mapped to one and only one shard. That means for every row, there will exist a shard in the system housing it, but also B, you're guaranteed that there is no way for that one row to land on two different shards. And in YugabyteDB, sharding is actually an automatic concept. So underneath the hood, the storage system takes care of sharding for you and ensures that all the tables that you actually generate have sharding built into them. Now, that doesn't mean you don't have control over it or you can't optimize it according to the types of use cases that you're dealing with, but by default, you will get some sharding applied to all the tables that you create in the system. And for the rest of the topic, we're going to be talking about the two big flavors of sharding that YugabyteDB offers: hash-based sharding and range-based sharding. So let's dive right in. What is hash sharding? In particular, we're going to be talking about consistent hash sharding because that's what we use in YugabyteDB. It is a form of spreading data across shards such that you uniformly distribute this data, and you also randomly distribute this data. So for example, if you think about a typical user table scenario where you have a primary key and a bunch of columns that are not primary key, we're going to be focusing on the primary key column or columns and essentially applying a hash function to that data in order to generate a value that will map to some particular hash range that we use internally. And each of those ranges would belong to a particular shard or tablet. I can go into a little bit more detail on the next slide, however. So let's say you have a hypothetical trivial table that is essentially a key value store. The key is your primary key and the value is what you're actually storing. Now you're trying to update or insert a new value for key K, insert value V. We look at key K, which is the primary key. We apply a hash function, some internal function that YugabyteDB uses for this, and we generate a hash key within a particular space. I'll talk about the space in a bit more detail afterwards. So let's say that you get key 1, 2, 3, 4. Now we look at all the shards we have in the system and we try to figure out which range does this hash key actually belong to. Let's say in this example, it belongs to shard 2 or tablet 2. That means that we know that this particular user request must end up being served by tablet 2. So now we can already forward this request all the way to the server that is responsible for serving user requests for tablet 2. And now coming back for just 1 second on the hash space. So we said that we apply a hash function and get a hash value. However, this space must be actually well contained. So we use 2 bytes for determining the hash space, which gives us essentially a range from 0000 to FFFF, which should be about 64,000 tables at max, if you assume that each hash value corresponds at most to, 64,000 tablets. In practice, that's perfectly fine, and we don't expect users to actually need significantly more scale. So maybe in this particular example, where we're looking from 00 to FFF, and we're chunking, let's say, into 16 tablets, we go from 0000, 0100, and so on and so forth. 16 tablets uniformly distributed, each taking care of 1/16 of all your space. Now, maybe a little bit of an example of how this looks like in practice. So this would be an SQL syntax example for a particular type of table operation. And let's focus on the left side first. So let's say that you're dealing with an application where you're processing user orders. Maybe it's like some shipping or some retail website. Fundamentally, you're trying to track these orders, and let's say you're trying to track like the physical address where it's supposed to be shipped and the email address of the person that ordered it. But your particular use case, and notice the hash keyword on the create table DDL statement here. So your particular use case might be that when you retrieve this data, you are looking to fetch orders by order ID. And also you'd like obviously to get to leverage the fact that this is distributed across your entire key space. So this would be a flavor of how you'd actually create such a table. But I also wanted to highlight that the primary key does not actually have to be a single column. It could be a compound primary key with several columns. And also it doesn't have to be only hash components. Despite this being hash sharding, we're still using the first component as the hash component, but we're specifying several components afterwards where we explicitly do not choose hash. And why is an interesting conversation that we can touch on in a bit. As I mentioned, the hash component dictates where exactly a particular row will land on a particular shard, which means that it also dictates which rows come together. So in this particular case, for example, we will get every row that has the same order ID landing on exactly the same shard, which, for example, for an application where you're trying to fetch all of the products contained in this order would be a valuable and useful property to actually respect in your database schema. Conversely, if you instead set product ID as hash, now for a particular order ID and a particular product ID, it might land on a completely different shard, even though they might share the same order ID.
And Bogdan, maybe I was going to share that this example on the right-hand side we see quite often, even for IoT-like workloads, where something like a device ID, whether it is a device emitting some data like a router or a shipment truck, for example, right, is the first part of the primary key, and then it's emitting data at a certain timestamp. So the timestamp is like the next part of the primary key, and all data for a particular device is together, and the timestamp part is like ascending because you're often doing queries like, show me the last 10 data points coming from this device. So this combination of hash and ascending organization, like clustered organization, we see quite commonly get used.
Yeah, that's a great point. And this is again like IoT is one use case. Retail was the use case that I was initially starting with. But indeed, like a lot of our customers are actually using this combination specifically to map their data to cluster their data in ways in which they can actually fetch multiple relevant pieces of information together efficiently. I'd like to also maybe go over some examples now just to showcase. I'm going to switch to my terminal real quick just to see if folks can you see this? Can you see my
Not yet. Not yet. It's still on the PowerPoint.
2 seconds. Let me fix this. And how about now?
Yeah.
Okay, nice. So I wanted to first highlight that I have a YugabyteDB cluster up and running here, which folks might be used to the UI here. And I've already pre-created a table just so that I can demonstrate how the hash sharding looks like. So I'm going to click through on this table here and highlight what hashing actually looks like underneath the hood. So this would be a single, this would be the hash space that we spoke about. And you see that there are 6 tablets here. And you see that for each of these tablets, they're responsible for a particular range of our entire hash space. So this goes from 000 to 02 AA, and then the next piece of the hash space and so on and so forth. So if we come back to our hash syntax, this was one of the tables that we created, and this is the second table that we created. And here in tables, you'll see that, whoops, demo day. You'll see that I haven't created those yet. So I was going to go to my terminal and just create those in the system so that you see how this actually looks like in practice. And then also the order details table, which takes hash and ascending for the primary key. Give it 2 seconds and refresh. There we go. So now we have our orders and our order details, and both of these have been created, and you can see it has a hash partitioning scheme here, and same for the order details, hash partitioning scheme. So really, even though it's a compound primary key, we're still talking hash partitioning. There's also one other thing that I wanted to mention, and maybe this should iron out the hash sharding. I mentioned up front that you as a user get control over how you shard your you get control over your sharding strategy. So in this particular case for hash sharding, by default we will shard into some factor of number of servers that you have in the fleet, but you can also explicitly override this. And first off, maybe this sentence requires a little bit of clarification. Why would you actually want to do this? And there's two parts to this. One is we want it to be a factor of number of servers because realistically your use case will grow. That's why you're using a distributed database. So as you add servers into the fleet, we would like to be able to leverage this moving forward. And second, this N is something that we also vary based on number of CPUs, because realistically, that controls how much work can you actually put on a particular Yugabyte cluster. And I think on the smallest deployment, we start with 2. That's why in my use case, in my UI, there was essentially 3 servers times 2, 6 tablets in total. I think we go up to 8 for like really beefy machines. So I'm going to just showcase real quick what this actually looks like, where we explicitly split this table into, say, 16 tablets. Just 2 seconds, go back to my terminal and pick this up. And you will see in a second, once it gets processed, I will go back to Chrome, refresh this, and you'll see orders 2 here. And if I scroll down, you will see a bunch of different tablets now showing up. I can just pick one keyword here, and you'll see 16 records of this. So now it has 16 tablets. Okay, so we've gone over the hashing component now as part of this. Should I switch over to range, Kannan?
Maybe one question, Bogdan. Is it possible for the users to kind of verify, like, 2 rows, are they in the same tablet or not? Is there some diagnostic observability?
That's a great question, and also something that obviously you'd probably want to care about as a user. So for example, one thing that we see users sometimes trying out is, hey, can I actually count how many records I get in a particular partition, or can I count how many records there are in total, but in a more efficient manner than just doing a complete scan? And yes, we have a means of accomplishing that. So first off, let me go back to my table and add a little bit of data into it. what was this called? Orders, I think. So take a while. So let's say select star from orders. I added some artificial data here. There's essentially 40 rows. All of them get incremental order IDs, and I added some physical address and some email addresses that are different. So now the way in which we normally select for this involves actually specifying the hash code that we use underneath the hood. So I have a handy little statement here, and I'm gonna go over that in just a bit. Can people see my screen well, by the way? Let me see if I can.
Yeah, if you could make the font a little bigger, it might be.
There we go.
Perfect. Yeah.
So what's happening here is I'm trying to run the same select star from orders. However, I want to specify, and this is a Yugabyte internal function. I want to specify that, hey, please compute a hash code over order ID, which is my primary key, and then look for how many entries there are in the hash space of 0 to 4096. And in this particular case, we get exactly one entry that gets distributed in this hash space. So this would be a way where you can either split the hash space yourself and start sending select count star queries essentially to different shards and do a parallel select count star implementation, for example.
Awesome. Thanks, Bogdan.
Nice. Let's go back to the presentation. Okay, so this kind of concludes the hash sharding. So maybe let's also dive into range sharding so that we can see the other flavor, and then we can at the end go over like a compare and contrast between the two options.
Actually, Bogdan,
so now,
maybe you would want to answer this specific question also that Dennis asked. They said, what's the best practice for the number of tablets depending on the number of nodes? Is this basically the question? I think is, should the user worry about the number of nodes in the common case, or will the system automatically take care of it?
So that's a great point. And I think this comes back to what I was saying about sharding being something that happens automatically in YugabyteDB. So we try to configure the defaults with which we start to be optimized for the system in which we're starting. So for example, let's say you start off with like a minimum 3-node RF3 deployment, and there are like some small machines with like 2 CPUs, then we optimize down the number of shards because your deployment doesn't need that much work. If you're talking like a 30-node deployment now with like 64 core machines on all of them, then we're going to try to optimize for a beefier use case. However, both of these assume that we're making the right or a decently optimized decision as a default. If, however, the status changes in the system afterwards, and say you're ingesting a bunch of data and you realize that, hey, I'm not getting the performance that I'm supposed to get for a particular shard, underneath the hood, Yugabyte also automatically does what we refer to as splitting. So splitting a particular shard into 2 constituent shards so that the system can actually make progress at the same performance that you were expecting beforehand. So realistically, the combination of these two lands on, we will make sensible defaults upfront, but if the status quo changes in the cluster, we will then continue to split these shards so that you can continue to get the benefits that you're expecting. I hope that answers the question. If not, like please follow up and we can continue.
Bogdan, there's one more question which was about, can you talk about how you're replicating shards? I know it's a slightly different topic, but maybe a sentence or two would be helpful.
Indeed. So yes, it is a slightly different topic, but it is somewhat related. So underneath the hood, Yugabyte uses Raft, which is a replication protocol. And let's say in a typical scenario, what we normally see deployed is, I want every piece of data to be replicated 3 ways. This is what I was referring to as a replication factor 3 use case. So that means that we take a table, we chunk it out in, let's say, like 16 tablets. Each single tablet then gets 3-way replicated. So actually for every tablet, there are 3 what we refer to as tablet peers. And those peers then get distributed across the cluster. And obviously we will do some sensible decision making there on, oh, don't put 2 peers on the same node because that kind of defies the purpose. Or, oh, please keep each peer in a different region because I have a geo-distributed geo-distributed cluster. We will probably be talking a little bit more about this in a follow-up section next week. So I would urge people to maybe like come back next week with similar questions and see if they get answered automatically by the speaker. But that's a great topic.
Yeah, indeed, Bogdan. Next week's topic is on resilience, which fundamentally is about like active-active and how it does replication. There's one more question coming for you, which is, is it possible to move a tablet to a particular node of choice?
Ooh, interesting. Right now, that isn't a feature that we're currently providing. We have an internal component that we refer to as a cluster load balancer, which automatically will shuffle tablets from one server to another based on load characteristics. So the intention there being that probably internally we know best what the characteristics are for individual shards, because this should be an internal mechanism that you as a user shouldn't be that concerned about. So for example, if a particular shard is growing extra large and we no longer want to split across the cluster, we might want to pin that shard to a particular server and then distribute multiple other smaller shards to other servers so that we match the load. And in the same spirit of Yugabyte is trying to optimize this for you transparently so you don't have to worry about it, we've chosen to make these decisions underneath the hood. I hope that takes care of that.
Yeah, there are some more questions, but let's go into range sharding and then I'll summarize the questions.
Awesome. So then let's go over range sharding, which is the second sharding mode that we provide. Now, in this case, data, unlike hash sharding, where we were uniformly and randomly distributing, here we're actually trying to match the user sorting of their input data. So if a particular set of rows in the input data were sorted one after the other, we would like, after they go through our sharding, to continue preserving that property. However, this also translates into it being hard for the system to make automatic decisions on to where to pre-split things for you and how exactly is the range of the data relevant. So for example, if you think of a low cardinality situation, like, I don't know, I want to have a primary key based on age. Like there's probably a limited amount of options for age that you want to consider in your database, which means that we should probably not decide to split between minus infinity and minus 1000 and so on and so forth. That should be something that the system should understand along the way, or you as a user should specify very concretely that I know what I'm doing here. In practical terms here, same applies. We take the primary key columns and then we try to map them to particular shards underneath the hood. And this is, I also wanted to highlight an example. So previously we had an example where the order details were hashed by order ID, but sorting by product ID in ascending order. So we can turn the exact same use case into an ascending. And this might be relevant for your application if, say, you actually are interested in getting the last n orders that have happened in the system. If that is a particular use case that you're trying to provide, then it makes sense for you to range partition based on order ID so that you get an efficient range scan on orders. Like in this particularly constructed example where I have actual price and quantity for my orders, maybe what you would like to do is get the total value that has been ordered in the last 100 items. This would allow you to actually execute such a query efficiently. And as I mentioned for hash sharding, where you have control over this, you will also have control of the initial split points in range sharding. We have a separate way of doing this, where you have to explicitly specify what the split points are. And this is, again, giving you control over, hey, I know what my input data looks like. This is exactly how I think that the data should be compartmentalized on disk. I'm going to switch back to my terminal real quick to showcase how this happens in the system, but then also to show you what the tables will look like in the UI. So first off, we create details range, and also, oops, I probably should have put the 2 here. Okay, so both of these are now in the system. And then if I switch back to my UI and go back to tables, now there's an order details range here. And you can see it starts off with 1 tablet. This goes back to what I was saying, that we don't know upfront what makes sense in a range partitioned world. So let's start off with 1 and let the system automatically split afterwards as more data comes in and we realize exactly where the distribution cut points should be. But if I go back and click on details range 2, you'll see now that there are 3 tablets. We specified, going back to the slides real quick, we specified 2 split points, which means that from your entire space, we will get 3 overall shards. And those split points are respected. So this is a little bit of an internal notation, but you specified 1000 and 2000. So here we go from minus infinity to 1000, then between 1000 and 2000, and then from 2000 to the end of the hash space.
Yeah, and basically, like just to explain that in a different way. Suppose your primary key is integer, and it's an order ID, and you want an ordered ascending organization of your data. Yugabyte wouldn't know whether it's good to make cuts at the 1 million, 2 million, 3 million boundary, or 1,000, 2,000. So in range sharding, often what you'll see is like what Bogdan explained. We start off with one tablet, and as data comes in, we rely on dynamic splitting to figure out where the cuts are and make the decision. And of course, if you know the domain of your keys, then you can use the explicit syntax to pre-cut the data. Thanks,
Exactly.
Bogdan. Yeah.
I guess the final thing I wanted to go over is essentially to compare the two so that we can round out the two strategies and to figure out.
Maybe one question before we do the comparison, Bogdan, is a lot of these decisions, are they applicable to indexes also, or do they only apply to tables?
Oh, that's a great question. So fundamentally in Yugabyte, indexes are also considered tables, obviously. So all of these considerations naturally map to indexes, but maybe a more fundamental point there is that you as an app developer will have to actually think about the use cases that you're trying to satisfy. So yes, Yugabyte does provide the same primitives on indexes as well, and I can showcase some examples, but it comes down to the same schema design exercise that you as an app developer would have to go through. So maybe let's take an example here real quick. Let me go back briefly. So let's say here on our orders table. So we have an orders table which has an email address. So let's say, for example, that you had a use case where you wanted to efficiently look up users by orders based on the email address that that a particular order came from. So let's say in this case, select star from orders. We have a bunch of orders, and then select star from orders where email, what I do here. So let's say a4@yugabyte.com. Okay, so let's say you wanted this particular query to actually be efficient. What you normally want then is that you create an index on this particular table that is hash sharded on the email address. So let me actually, I have an example of something like that.
Maybe we can start with like an explain, which shows that right now it's not.
That's a great point. So let's say if I do an explain, you'll see that this is essentially a sequential scan of orders. Like orders has a primary key on order ID, which means that we don't know how to efficiently look up which email address, like which of the rows that I have in the table has email address A4. So this is where naturally you'd actually want to create an index, but you'd want this index for this particular type of query. You'd want this index to be able to let you efficiently go and look up this one row that that you know the complete value of. So in this case, let me see if I correctly copied this. So I want to create an index by, let's do, for this particular case, let's do hash. So I want to create an index on orders by email address, but hash. Give it a while. 2 seconds. This is also on my Mac, so please discount the, yes, okay. So now let's try to do the same explain plan. Okay, so this now gets us exactly what we're looking for. So it is doing an index scan on orders, and it's explicitly looking it up by this this ID.
So a relevant question has come in from Kurt. The question is, are secondary indexes also sharded? So maybe you can show us the split scheme, whether it's applying to indexes also, and does all the pre-splitting and dynamic splitting, all of that makes sense?
Great question. So now we're going back to the UI here, and we have user tables at the top and index tables. These are technically also still user tables, but you can already see the order by email hash. So, and if I click through on this, you will see that it also has 1, 2, 3, 4, 5, 6 tablets. So as I mentioned previously, for hash sharded tables, we're looking at 2 as a factor of number of servers, and I have 3 servers in the system, so 6 tablets. So this index is essentially treated as a normal table that is hash split. So then a hash partition. So then it's getting 6 tablets up front. And this is what you're seeing here.
Got it. And suppose instead of looking up by the exact email address, I wanted to search for all email addresses that start with A or A to B, then what?
Yes.
What is
So let's say that in this case, we're talking with email address less than B. Let's say that this was normalized and you knew that all your email addresses are lowercase and so on and so forth. Now, again, because we don't, so now you'll see that again, it's back to doing a sequential scan on orders. This is because we don't have an efficient way of determining all the rows that fit this pattern. We're using a hash function, so then there is a random distribution in the index that we have created. So now we go back to our index and say, okay, let's create an ascending index, and let's also modify this and call it range. So also an index on orders, but by email address. Give it a bit. And then we'll run the same explain plan on email address less than B. So now you'll see, now it's back to using an index scan, and it is using the range index on orders for this condition. And I can go back and do the same exercise we just did for hashing, just to validate. If I refresh the set of tables in the UI, you will see the new index appear here. And if I click on it, because it is range partitioned, it gets one tablet. And as we were mentioning about normal user tables, dynamic tablet splitting will apply just the same to indexes, because underneath the hood, we treat them as normal tables. So as your data in the index table grows, they will automatically get split and further distributed on the rest of your cluster. And this applies the same for both hash and range.
Perfect. I think your last slide anyway was going to summarize the trade-off between the two. I think that would be great, Bogdan.
Yes. So essentially, if we go back to this, there's maybe like 3 characteristics on which we'd like to split the problem here. So one is pre-splitting. We want to actually prevent what's called the database warming problem. Like as we're inserting more and more data into it, let's say if things were range partitioned and you're partitioning by timestamp as an example that Kannan was using earlier, and you're constantly using now, clearly like the most recent data will keep on moving further and further to the right, which means that your the shard which is at the right of your space is going to get more of the data. So we're going to want to pre-split the data, which technically both hash and range tables actually support in Yugabyte. But in range, really, we don't know what the correct space should be that we should split the ranges into. The second property is performing range scans efficiently when we're talking about large amounts of data, and this is where actually range sharding is the valid choice. It actually allows you to do efficient scans between point A and point B, whereas in hash sharding it's uniformly distributed, so we don't really have an efficient way to pick up a contiguous chunk of data. And finally, hotspots. So in one of the problems that we end up seeing is that as your user traffic is different based on your distribution of data, or based on, let's say, some accounts, some user IDs or some account IDs having more data, you're going to end up with a hot shard problem where the particular shards underneath the hood which support that particular heavy user in your social network, or that particular account ID which runs more ads through your system, that particular shard is going to get more traffic, which means we need to be able to split that data efficiently so that we get rid of your hot shard problem, which is much more amenable to a hash sharding scheme than a range sharding scheme. And combining this, what we ended up deciding in Yugabyte is that hash sharding ends up giving us most of the benefits we want as a default scheme in the database. So most of the use cases we're talking, whether it's like IoT or retail or ads and so on and so forth, most of them are able to leverage hash sharding as a default. However, there are plenty of valid use cases for range sharding. And that is why we wanted to ensure that range sharding is an option that the user can select at will, because they know better what their access patterns are, data distribution, and so on and so forth. So that's why we've chosen hash sharding as the default mode for all our tables. However, we're providing range sharding both for tables and indexes as a user controllable setting.
Thank you, Bogdan. I know there are 1 or 2 questions. Maybe we are a little bit over time, but we would be, let's take 1 or 2 questions from the live stream right now. But one announcement I just wanted to share is the Slack channel that you see on the slide, yugabyte.com/Slack, and the YFTT sub channel for YugabyteDB Friday Tech Talks. You can feel free to continue posting questions there. But let's take a couple. So one of them, Bogdan, if you could go back to the split at syntax for range sharding.
Oh, yes.
A question was,
Yes. Range. Sorry. Yes.
Yeah, like a question was, what happens if the values don't fall into the range? Then where does like if values do not fall into the range, then where does the tablet goes? I think their question is like, is there a problem with the syntax? Like suppose the user passes 500, does the syntax allow any gaps?
So one thing that, one thing that is not represented here is that actually you could, let's say we're talking integers, you could look at this as a continuum from like minus infinity to plus infinity. It's just that in this syntax, we actually don't represent the edges of this segment. So really, if you were to pass 500 here, it would actually go into the minus infinity to 1000 bucket. That is how you could think about this. Correct. So really, there is a continuum on which we are splitting. We are just applying a number of cuts on this continuum, but we're not showing the final edges. So you could think of the final edges as being part of this this split mechanism.
Yeah. So the case that the question was worried about should not happen, because there are two entries here, but essentially you have created three ranges from minus infinity to 1000, 1000 to 2000, and 2000 to sort of. And it's data type specific. So, but all values for the data type are covered. Yeah. Let me see if we can take one more question. How fast does dynamic split complete, and how does it affect the ongoing transactions? The great question. Yeah.
Oh, great question. So maybe we'll start with the second one because that's easier. So for ongoing transactions, you should not necessarily see a problem because we will retry underneath the hood. So if a split does happen and say you had an ongoing transaction to this tablet and this tablet now is split into two components, our internal transaction manager and the internal client that we use should detect that the split has happened and should retry the operation if necessary, or should now go to the respective children of this tablet in order to fetch the corresponding results. If, however, this operation takes more time than expected or more time than your timeout, let's say you had an extremely small timeout, like some number of milliseconds, you might end up seeing a user error because of this with a respective message that, hey, we have had to split this tablet and we couldn't serve this request within the timeout that you specified. As for how fast this happens, the actual processing of the split operation should be on the order of our RAF timeout, which is like 3 seconds, I believe. However, there will be background work after the fact to get the system back to an optimal state. So for example, we are trying to do this operation fast up front, but then we're offloading a lot of compute behind the scenes after the practical operation has happened. And that will depend on the size of the input table that the input tablet that we were trying to split. Because essentially we'll be doing what is called the compaction process behind the scenes. So it's really dependent on the total amount of data you have in the system.
Yeah, so basically the heavy lifting is really in the background, and the instantaneous cut is really producing like logical half sections, like the upper half section of a tablet and lower half section in a very quick real-time operation, and then the rest of the happening in the background. But that ties to one other question. Maybe that's the last pending question we have not answered, and let's see if we can get to it. It's like, I think the question is around like, is the tablet placement somewhat static or is it adaptive? And it ties into two questions, like what happens if I add a node? Do only new tables get the benefit of that new node, or do we do any rebalancing? Yeah. And number two,
that's a great question.
Based on like, I think they were asking whether, is it based on any learning model or is it kind of a simplistic scheme, right? Like, so.
Oh, I see. Okay, maybe again, we'll start with the second one. It is relatively simplistic in the sense that we have encoded heuristics ourselves based on the learnings that we have had from past experience, customers, and so on and so forth. There is no machine learning model underneath the hood right now driving this. As for what gets affected by this, new tables, and so on and so forth. So this mechanism applied, there is a component that I mentioned earlier called our cluster load balancer, which takes care of managing the policy and the actual implementation of where tablets actually get placed on which servers, what happens if servers die, what happens if servers get added to the fleet, how do I keep the system in perfect balance given the constraints happening right now. And this will function for every table in the system, and it will happen as a background operation pretty much every second. We will look at the distribution of tablets to live T servers, and we will compute if there is any level of improvements that we can do to our tablet placement policies, and we will shuffle those. And for example, in the case of tablet splitting, we're going from, we used to have one tablet here, and now we have two, which most likely will trigger some form of imbalance in the system. and that will trigger the load balancer to kick in and say, oh, these 6 tablet peers for these 2 child tablets now overload these 3 servers on which they're on. Let me try to move some of them off so that I can bring the cluster back to a balanced state. I hope that covers that. But if not, please like join along and follow us on the Slack channels, and we can continue this conversation offline.
Thanks, Bogdan. And thank you to everybody that joined and asked really interesting questions. I know there's one more question that came up. I would request Omer to kindly post that question on the Slack channel because we're kind of well past time. But thank you, everybody. See you next Friday. And the topic is really about availability and resilience, and it covers aspects like replication and so on. So we'll talk about those aspects of YugabyteDB next week. Karthik and Rob Sami will be the people from Yugabyte talking about this. So please check out our next Friday Tech Talk. Thanks a lot, Bogdan.